let's let's see another important topic called recursive. Recursive. Okay. Um, to understand what is recursive, the best way is demonstrate by example. But to explain the recursive, it is a function that call itself. Okay. A function A, within the function A, we also call another, not another, we also call function A. So in the definition of function A, we also use in function A. Okay? So in the big bracket of function A, we also use in function A again. This is called recursive. Okay? Let's see an example of the a to the power of whatever, a to the power of I. Okay? A to the power of I. So for simplicity, I is an integer variable, and A is a double variable. Okay, so we're going to define a function. Okay, this function is calculated with A to the power I. So we call this function power. Let me directly type in Visual Studio. So we are going to define a function called power. Okay, and the first argument, power, okay? And the second argument is integer, I, okay? So, and you will return power. Maybe power is something in the library already, maybe. So you kind of give me this strange underline. But anyway, maybe we try. Or we call it my power. Okay. My power. Okay. It still give me the trouble. Okay. Why? Anyway. In here, we define my power. The first argument is A, and the second argument is I, which is integer. I, and the return type is double. So okay. So now, how we calculate the A to the power I is we're going to use a for loop, which will need an integer k, and the result is the calculated result. So we start with 1.0. And how many times we're going to multiply a value? We're going to multiply I time. So for k is equal to 0 until k is not less than I. And each time k plus 1 increase by 1. Okay? Now, result, which is starting from 1.0, result times equal to A. So this statement is equivalent to result is equal to result times A. And this kind of result times result, a result equals result times A. Initially, we have a result with the value of 1.0. So this should be small form. Anyway, okay, now we define a function called myPower and a return result. Okay, we define the myPower here, and we declare myPower here, and in main we are going to get a value of I and the value of A. So the second one is digit, okay? The first one is getting A. The second one we get in integer value of I. Now, the result is what? We are here we are calling the function of myPower, which I just designed this function called myPower. MyPower will give two arguments. One is A, the other is I. Okay? So it means that okay? So we use a cap to represent power. So we're using cap. Cap, where's a cap? Where's a cap? Here, cap. Not the Chinese cap. Percentage D is equal to percentage F. And we are going to print I. And we get the result. The result is this I is not double. This I is integer. So I is integer. Okay? Now, the first line is to get two values. One is floating point, one is integer. And then the second line we call in the function myPower, which computer will execute to here. Okay, declare a function, declare a double variable, declare integer variable, and then assign 1.0 to result, and then running this for loop. Okay, so A represents the number of times we're going to multiply A to the result. And initially we put 1.0 to the result. And then this for, we multiply A I time, okay? I times, okay? Depends on what value you are going to put in this myPower, okay? So now let's give it a try of this program. Okay. So let's compare. Let's run it. Okay. So what we are going to compute 3.0 to power 3. So it's 27. Okay. So we got this 9. Okay. 3 to the power 3 is 27. How about 2 to the power 10? It should be, I think, 1024. Okay, yes, we got 1024. Okay, 1024. Okay, so let's save this version of program. This is a common way of calculate the power. Calculate power. Okay. Let's save it as EX12-06A. Now, the second version of this example is to use in recursive function. Why recursive function? As we know, say for example, 3 to the power of 5. Okay. 3 to the power of 5 is equal to 3 times 3 to the power of 4. And 3 to the power of 4 is equal to 3 to the power of 3. And 3 to the power of 3 is equal to 3 times 3 to the power of 2. And 3 to the power of 2, 3 squared, is equal to 3 times 3 to the power of 1. And 3 to the power of 1 is equal to 3 times 3 to the power of 0. And once 3 to the power of 0, we know it is equal to 1. Okay? So what we see here is that something to the power of something is equal to something to the power of something. 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 Until something to the power of 0, which is 1. Okay? So we can design a function called recursive power. Okay? This function will be looked like this. We declare a function called recursive power. Recursive power, okay? Now, this function called recursive power. This main function, we are not going to change anything, okay, in this main function. Or we have to change because we are going to use different power function called recursive power. We just change the function we call. Okay, now the function is called recursive power. Now here we are going to fully define recursive function. Okay, now in the recursive function, the result is we are not going to use this for loop. We are going to use what we observe from what we see from this whiteboard. Okay, we are going to use what we see in this whiteboard. What we see in this whiteboard is this is a power function. This is 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 power function. And this power function call this power function 3 to the power of 4, calling the same function with different argument. 3 to the power of 3. 3 to the power of 3 calling 3 to the power of 2, calling 3 to the power of 1, calling 3 to the power of 0. Until 3 to the power of 0, we know exactly what's the answer, which is 1. And this 1, we call it grounding condition. Ground means floor. Grounding means the bottom, okay? Grounding condition. we all the way down to here. We stop here. When we stop, we call this condition is grounding condition, which is also called in 3 power 0 is grounding condition. So in your recursive function, you must have a grounding condition. Okay? So what we do is this. If I is equal to 0, we return 1.0. Okay? This condition check, this if statement represents the grounding condition. Okay. If I is not equal to 0, what we're going to do is doing this. Else we return. We return A multiplied by recursive power of A I minus 1. Okay? And this end our story. All we need to do is like this. Okay? In recursive power, we call in recursive power. In recursive power, we call recursive power. Recursive power, call recursive power. Here. Recursive power, call recursive power. And this recursive power calling this 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 recursive power. And this recursive power run into grounding condition. So it stopped calling recursive power because it run into grounding condition. And this grounding condition is necessary. It's must. Okay? It's a must for writing recursive function. Otherwise, you will go into an infinite loop. Okay? So we have done the program. We built. Okay? And we run. 2.0 power to 10 is 1024. Okay? So we got the correct answer, I suppose. Okay? Wrong again. 3.0. 5. Okay, is 243. Okay? 243. Right? Right? Yeah, I suppose. Okay, let's save this program. This is a first example of recursive function. And recursive function, I should say, is a very important feature of C. And you know how to do recursive well, C become a very, very powerful language. It would allow you to do many complicated jobs which other language cannot accomplish. Okay. Another example, which is also very commonly used to illustrate recursive power, which is the factorial. Now, everybody know what's factorial. So, for example, 4 factorial is equal to 4 times 3 times 2 times 1. And 5 factorial is equal to 5 times 4 times dot 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 times until 1. So what is 10 factorial? It's 10 times 9 times 8 times 7 times dot 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 until 1. So everybody knows what's factorial. But in computer, how can we do factorial? And using recursive function? Because if we using 5 factorial as to demonstrate, 5 factorial is equal to 5 times 4 factorial, right? And the 4 factorial is equal to 4 times 3 factorial. And the 3 factorial is equal to 3 times 2 factorial. And 2 factorial is equal to 2 times 1 factorial. Okay? Now, 1 factorial, as we know, is equal to 1. So, factorial calling factorial, factorial calling factorial, factorial calling factorial, factorial calling factorial. Until what? Until 1 factorial, we know the answer is 1. And this one is grounding condition. Okay? It's like we jump 1 step down, 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 and until we run into the floor. And no more place to go down. And it's a must, otherwise you go into infinite loop. So we design this factorial program. We just call, this time we define this factorial program in the first portion, as a first function. So we call it fit. And we're using, because factorial is, the number is large, the numeric number will be very huge. But we suppose we will not go to that big, so we're still using integer. So fat integer n. Okay, if n is equal to 1, we return 1. Else, we return n times factorial of what? N minus 1. Okay? Imply that what we do here is n factorial. N factorial is equal to n times n minus 1 factorial, right? 4 factorial is obtained from, 5 factorial is obtained from 4 factorial. 4 factorial is calculated from 3 factorial. 3 factorial is calculated from 2 factorial. 2 factorial is calculated from 1 factorial. Okay, so n factorial is n times n minus 1 factorial. So the recursive function is just something like this. So we get a value. This time we only need a value, and this time the result is integer. Okay, the result is integer. Okay, so factorial we call factorial. So percentage d factorial is percentage d. Okay, so it's kind of very easy by writing this way. Okay, using recursive function maybe the easiest way to do some job, to easier to program, as long as you understand the problem. Okay, as long as you understand the recursive relation. Okay, once you got the recursive relation, you can write it in recursive way to do the job. So it's easier to write this function and to compute is easy. Okay, so now factorial phi, input phi. So phi factorial is 120. Okay, am I correct? Maybe we'll do a little check. Phi factorial is phi times 4, which is 20, and times 3 times 2 times 1. This is a 6. 6 times multiplied by 20 is 120. So I suppose our recursive program is correct. Okay? So we save this version to calculate the factorial. Okay? Now, if we so EX12-07A, if we do not do it in recursive way, supposedly we want to do it in more conventional way. What I'm going to do is rewrite this factorial function. And the conventional way to do this is using for loop, right? When you first run into, you want to calculate a number's factorial, the first thing hit your mind might be you using the for loop. Okay, using for loop. So I is equal to n. Okay, and we should have a result first. Okay, when I set initially to n, and when I is greater or equal to 1, and each step minus 1. So initially we should set the result to 1. Okay, now in here, in the first step, the result is multiplied by I. Okay, so the second time multiplied by I minus 1, the third time multiplied by I minus 2, the fourth time multiplied by I minus 3, etc. until I is greater or equal to 1. We'll stop. Or maybe I is greater than. As long as I is equal to what? To 0. Okay? Maybe it's easier to understand. We always do this multiplication, cumulative multiplication. Okay, each time we decrease the integer variable I, and the integer variable I is starting from n. And once we complete this for loop, we return the value of result, and we complete the job. Okay, And this is a much more conventional way to do it, using regular for loop to do the factorial. Okay, so this is probably the first version of program when you see this assignment, when you see this programming task, and it's easier to understand. But in fact, if you use recursive version, it might be easier. Okay, for me, recursive version is easier. Okay, now find. Okay, 5 factorial is 120. So this version of factorial function is doing the identical job for the recursive version. And this version is using for loop. I should say, in terms of program efficiency, this version is faster. But for a mature programmer, I should say, normally a mature programmer would prefer use the recursive version because it's easier to program. Now, however, let's say this version of factorial first. Okay, now EX12-07. Okay, now I'm going to do is making another example. Suppose F0 is 1. F1. Now we're starting from 1. F1 is 1. F2 is 2. And Fn, not 2, okay, is 1.5. Okay, and Fn is 0.9 times Fn minus 1 plus 0.5 times Fn minus 2 for n greater or equal to 3. So F1 is defined, F2 is defined, and the rest of Fn greater or equal to 3 is also defined. So how I'm going to ask is F10 is equal to what? When we define Fn is defined by Fn minus 1 and Fn minus 2. Okay? So what is F10? At least we have 3 versions of it. We have 3 versions of program which can calculate F10. We have 3 versions. I should say, all come up with a correct answer, but they are different. For engineering, for IE engineering, once we have a problem, once we have an issue we should take care of, we will come up with a number of options that we can take. Now, which action you should take. Okay, it depends on the environment. It depends on the current situation. Okay. Similarly in programming, these three versions all come up with the same correct answer, but they both have pro and con. There's a trade-off involved in choosing which version we should use. Now, the easiest version that we come up with using what? Using array, using double array to do this job. Okay? Now, let's use double array. We have 10 minutes left in this class. I may not be able to finish all three versions of this program, but let's try how many versions we can do before the end of this class. Now, we declare a F array because we are going from 0 to 10, F0 to F10, so F1 to F10. So we don't, F0 is not an issue here. But when we declare an array, it always starts from F0. The way we can do is we declare a double array of size 11. When we declare size 11, it means the index is 0, 1, 2 until 10. And we use 1 to 10 and forget about the F0. Okay. It might be easier to program. Okay, we don't need F0. So we declare a function with size of 11. Okay. Now we are going to do is using for loop. Before for loop, we know F1 is equal to 1.0. And F2 is equal to what? I forgot. F2 is 1.5. F2 is 1.5. F medium bracket 2 is equal to 1.5. Now, we need a for loop. I is equal to 3 until I is less than or equal to less than or equal to 10, right? And each time I is increased by 1. So we need an integer variable called I. Now, for each for loop, we calculate Fi, which is equal to, I forgot, 0.9 times times Fn minus 1. 0.9 times Fi minus 1. Okay, in program we should use I. And plus 0.5 times Fi minus 2. Okay, so the for loop has to be calculated in this way because where's my whiteboard? Because now when we calculate, initially we have a F1 and a F2. Now what we need is to calculate F3. F3 is based on F1 and F2. Okay, we have a formula for that. Here we have a formula for F3. So once we got F1 and F2 and F3, we can calculate F4. F4 is coming from F2 and F3. Then we have to calculate F5. F5 is coming from F3 and F4. And F6, we have to calculate. We're coming from F4 and F5. So the computation sequence, the computation order should be, we compute 3 first, then compute 4, then compute 5, then compute 6. Okay? So before we have a 4 and a 5, we cannot compute 6, right? So etc. and so on until we got F10. F10 is coming from F9 and F8. These two numbers, okay, to get F10. So we're kind of using memory space by declaring array to do this computation. So at the end of the program, we print F for our final result of F parentheses 10 is equal to percentage F slash n. And we just print F10, this double variable, we get the final answer. So, okay? So, we built, run it. Okay, it's 10.99949 and 62. Okay, now it's a little bit difficult to figure out this algorithm to compute F10. However, we still want to save this program. We save it as EX12-A-0AA. Okay, now the second version, which I think is easier but is not efficient, is using recursive function. Okay, it's using recursive function. How recursive function use is when we have a F, when we want to get F10, we need to calculate F9 and F8. When we need to calculate F8, we need to calculate F8 and F7. When we need to calculate F7, we need to calculate F6 and F5. So let's keep doing this because we already given F1 and F2. And F1 and F2 is our grounding condition. It's the bottom of this problem. So what we're going to do is using recursive version. And it's kind of easy. Very easy. This function is called F function. We gave it an integer called I. Now, what we're going to do in this F function is we have to check if I is equal to 1, we return a value of what? Compared to the breadboard, compared to the whiteboard. F equal to 1, we return 1 here. Okay? We return 1. Return 1. Okay? Else, if I is equal to 2, which we return 2.0, right? Check on whiteboard. Or not 1.5. Okay, return 1.5. 1.5. Now, else if not equal to 1, not equal to 2, we return what? 0.9 times f with I minus 2 plus 0.5 times f I minus 2. This is I minus 1. Okay? 0.9 times I minus 1, 0.5 times I minus 2, right? Supposed to be correct. Yeah, 0.9 I minus 1, 0.5 I minus 2. So, in main, what we should do is easy. We just call the function by giving 10. F is a function, okay? We don't need all this variable. We don't need all this stuff. We just, in the main function, we call function f. F is a function name. It get integer value 10, okay? And then you will do all of this sort of stuff, okay? We'll call F is called recursive. Now, we build a function. Let's run it. So F10 is equal 10.99949 and 62. So we get the identical result as the previous version. Now, we save this version of the program. This is called the version B, EX12-0A B. Okay? So, how about the third version? The third version is the most difficult one, but it's the most efficient one, and save the most memory space. But the price is it's difficult to write the program. It's difficult to write the program. Okay, this recursive function is most easy one, but it have overhead. The overhead is it takes longer time to execute because in this small program we only run F10, but you run a bigger program like F1 million. Okay, this recursive version is run the slowly, take much longer time than the first version. But now I'm going to write a very efficient one, a version that saves many space. This version is at least double with F underline 2 represent F minus 2, okay? And F underline 1 represent F n minus 1. And also we have a F, okay? We have 3 variables only. Now, we starting with F underline 2, okay? Which is equal to 1.0. And F minus 1, which is equal to 1.5. And this is in fact F1. This is in fact F2. Okay? Now, similarly we using Fn fi equal to 3 and I less or equal to 10, okay, and I plus plus, we still require an integer variable I to count the number of times we are going to compute. Okay, now, so f is equal to 0.9 times f underline 2, right? Or underline 1. Let's see. Okay, f underline 1. And then plus 0.5 times f underline 2. Okay. So once we done this, the new f1, f underline 1, will get the value of f. And the new f2 will get the value of f underline 1. So the order of these two statements is very important. The order right now is wrong. We should flip these two statements order. F2 should get the new value because we kind of moving forward one position. So we F1 become F2 and the F become F1. So F1 should give away the value first before it take on a new value. So once we done this, we just print F. And hopefully we do it correctly. Okay? Just hopefully, because I programmed it in the very, very, very fast. I might make some mistake, but the result is correct. Okay? So what I'm going to say now is that if you have a programming test to do, you need to think. There are more than one way to write a program. And in this program, when you write a program, what's your limitation? You need speed, or you need readability, portability. You want to write your program easier to understand, or you want to write a program that run very fast, okay? Or you want to run your program using the minimal amount of memory space, okay? What I'm going to say is this program is the most difficult to understand. This version that I just writing now is the most difficult to understand, but it takes less space. You only take 3 double variable and 1 integer variable. And using for loop is very efficient. Okay? A function call another function. There's overhead there. Okay? Even in today's computer, the overhead is minimal. But if you call it too many times, it's kind of doing duplication computation. So even the recursive version, the second version that I wrote is very easy to understand, but it's not very efficient. But this version is not only efficient, but also using minimal amount of memory. But it's not easy to understand. is difficult to write. Even me, I have to be very careful to make mistake in writing when I wrote this program. But fortunately, it is correct. Okay, I run it again. F10 is 10.999962. Okay, all three versions come out with identical answer. Okay, all three program is correct, but the amount of resource used, okay, the readability, anything, any consideration is different. So this, by doing this example, this is the perspective that I want to emphasize to let you guys understand. So, yeah, so I made the copy of this program, and you guys do not have a question, the class is dismissed. Okay.